Hello, I'm Tom Buchholz. Welcome to this presentation, Elementary Particles, Dark Matter, Dark Energy, and Observable Properties. This presentation follows an outline for a scientific paper. This video talks about highlights. You can pause the video or return later to view visual details. Introduction. Goals of this work include cataloging elementary particles, specifying dark matter, describing dark energy, and cataloging properties of objects. Each one of these goals associates with an 80+ years old physics challenge. Making progress toward the goals can help explain data. The work includes so-called new modeling, which has roots in popular modeling, uses solutions to integer arithmetic equations, and along with popular modeling, suggests explanations for data that popular modeling alone seems not to explain. Given that the challenges are at least 80 years old, you might ask, why now? Today, there might be enough data to evaluate models that try to make steps toward the goals. Some of the data pertains to observed ratios of effects that popular modeling does not attribute to ordinary matter, to effects that popular modeling does attribute to ordinary matter. And there's other data, for example, about large-scale aspects such as the expansion of the universe. Method. The method aims to explain data and to output lists, such as of properties of objects and of elementary particles, that popular modeling, in effect, inputs. The following are some underlying notions. Some of the electromagnetic ratios might point to non-ordinary matter atoms that have bases in right-handed elementary particles. The density of the universe ratio might suggest that there are, in total, 6 isomers of most known elementary particles. Multipole expansion techniques might help explain the rate of expansion of the universe. The math features integer arithmetic equations of the form S equals a sum of terms. Each term is a unique positive integer k times S sub k, which is either +1 or -1. Solutions come in pairs, in which each solution is the negative of the other solution. New modeling interprets sigma equals 1 to associate with electromagnetism. Sigma equals 2 associates with gravity. A number, 1, of terms in the sum associates with notions of monopole potentials. 2 associates with dipole, and so forth. The sign of S links to polarization mode. For sigma equals 0, some solution pairs associate with families of elementary particles. New modeling suggests that there are 6 isomers of all elementary particles except for the photon and any other long-range interaction elementary bosons. So-called isomer 0 associates with ordinary matter. Isomer 1 through isomer 5 associate with dark matter. Across the isomers, counterpart elementary particles have equal masses. Isomers can differ based on handedness and based on counterpart flavors for leptons. As a result, isomers 1, 2, 4, and 5 stuff evolve differently than do isomer 0 stuff and isomer 3 stuff. Extrapolating from Lorentz invariance suggests that monopole and quadrupole gravitational solution pairs associate with attraction, and that dipole and octupole solution pairs associate with repelling aspects of gravity. New modeling suggests that there are 6 instances of the property of charge and the related property of charge current. Ordinary matter does not sense dark matter charge, though ordinary matter does sense other dark matter properties. There is one instance of the property of energy. The reach of the related aspect of gravity is 6 isomers. The one instance of energy treats all isomers equally. Results. This table suggests an analog for elementary particles to the periodic table for chemical elements. Some sigma equals 0 solution pairs associate with all known elementary particles. Other solution pairs link to elementary particles that new modeling suggests. Suggested new particles include an inflaton, which some cosmology anticipates, a graviton, which people tend to anticipate, and a so-called J boson, which new modeling suggests associates with the Pauli exclusion principle. Notions above might suffice to explain data above or to help close gaps between popular modeling and such data. For example, new modeling suggests that each of many galaxies starts based on reach 1 attraction as a 1 isomer halo. The galaxy might repel based on reach 2 repulsion, 1 other isomer. Later, the galaxy might attract enough stuff to exhibit a 4-to-1 ratio of dark matter to ordinary matter. A galaxy that associates with many mergers can exhibit a 5+1 ratio. Or, regarding the rate of expansion of the universe, one might improve popular modeling by using the notion that use of an equation of state that well fits data early in the previous billions of years era could extrapolate to underestimate later repelling regarding neighboring objects. Or, the 1-to-1 ratios regarding light associate with a reach of 2 regarding atomic states and with the notion that cosmic electromagnetic background radiation formed via atomic transitions. Discussion. Other results associate with new modeling. New modeling points to relationships between values of properties such as spin, charge, and mass for elementary particles, and to a relationship between the strength of electromagnetism and the strength of gravity. New modeling suggests rest energies for at least 2 neutrinos of 3.4 hundredths of an electron volt, and so forth. New modeling seems to provide a basis for cataloging aspects discussed above and also for cataloging conservation laws. New modeling points to a possible progression that could result in extending new modeling techniques to have relevance regarding so-called topological materials. Conclusion. New modeling enables progress regarding cataloging elementary particles, specifying dark matter, describing dark energy, cataloging properties of objects, and explaining data that popular modeling alone seems not to explain. References. The items listed here provide additional breadth and depth. Thank you for viewing this presentation, Elementary Particles, Dark Matter, Dark Energy, and Observable Properties.